All right, today we're diving into a real scientific detective story, deep inside the atomic world of steel. Our mission? To solve a puzzle that has stumped metallurgists for almost 100 years. The mystery of how one of steel's most important structures actually forms. Now, this might look like a piece of abstract art, but what you're seeing here is something called bainite. It's a key ingredient in some of the toughest, most advanced steels on the entire planet. That beautiful, needle-like structure is the secret to its incredible strength. But how it gets that way, well, that's been the subject of a very long and very heated debate.
And this is where we get to the heart of the mystery. See, when steel transforms into bainite, the reaction kicks off, it gets going for a while, and then it just stops, dead in its tracks, long before it's actually finished. It's a phenomenon called the incomplete reaction. And for decades, nobody could really explain why it happens. It's kind of like a fire that just decides to put itself out.
So, to crack this case, we've got to get right to the heart of the scientific argument. And it really all boils down to two completely different ideas about how atoms rearrange themselves. Is it a sudden, disciplined snap? Or is it a slow, messy shuffle?
This is a really great way to think about it. The snap theory, what scientists call a displacive transformation, is like a highly coordinated, almost military-style maneuver. All the atoms shear into new positions in a split second. This is so fast it actually traps other atoms in place, especially the bigger, slower ones. The shuffle, on the other hand, or the diffusional theory, is the total opposite. It's a slow, random migration where every atom has plenty of time to move around and find a new home.
So the leading theory, which was first proposed by a scientist named Hegeman, is actually pretty clever. He suggested it's a two-step process. First, a plate of bainite just snaps into existence, completely diffusionless, trapping a ton of carbon atoms inside. And then only after that super fast growth does the trapped carbon start to leak out into the metal around it. And here is the absolute key to the whole thing, a concept called the T0 curve. You can think of it like a thermodynamic point of no return. For one of those snaps to even be possible, the final structure has to have less energy than the starting one. But as that carbon leaks out of the bainite, it enriches the surrounding material. Eventually, that surrounding material crosses the T0 line, and at that point, another snap becomes thermodynamically impossible. The energy advantage is just gone.
Okay, so if this theory is correct, then that T0 line should act like a hard wall, stopping the reaction cold. All we need now is the proof, the smoking gun. So check this out. This chart shows the prediction perfectly. The theory says that as bainite forms and spits out carbon, the carbon concentration in the metal around it, the austenite, goes up. You see it moving to the right on the chart until it hits that solid line. That's the T0 prime line, our thermodynamic wall. Right at that point, the reaction should just stop.
And boom, here it is. This is the smoking gun. This chart brings together data from over 150 different experiments. The vertical axis is a ratio. It's the measured carbon level where the reaction stopped, divided by what the theory predicts it should be. A ratio of 1 means a perfect match. And just look at that cluster. The average is almost exactly 1. The experiments show the reaction stops right where the theory says it has to. It's a perfect match.
But believe it or not, that's only half the story. If this transformation is a sudden snap, it shouldn't just trap the little, fast-moving carbon atoms. It should also freeze the big, slow-moving atoms in place. So, let's see what the evidence says.
This is just incredible. What you're looking at is data from something called an atom probe. It's a machine that can literally count atoms one by one across the boundary. And what does it show? The concentration of heavy atoms like molybdenum and chromium is completely flat. No spikes, no dips, nothing. They are frozen solid. This proves the transformation happened way too fast for them to even think about shuffling around.
So when you put these two huge pieces of evidence together, the thermodynamic wall and the atomic freeze, the conclusion is pretty much inescapable. Bainite forms in a sudden, diffusionless snap, and the carbon only moves around afterwards.
But hey, in good science, you don't just prove your own theory. You have to show why the others are wrong. So let's put on our myth-busting hats for a minute and take a hard look at the other contenders.
Okay, first up, we've got a major alternative theory called the negligible partitioning local equilibrium model, or just NPLE for short. It tries to explain things by proposing that something really specific and weird happens right at the edge of the growing bainite.
The whole idea here is that as the new bainite plate grows, it pushes other atoms like manganese ahead of it, creating this tiny, razor-thin spike of high concentration right at the boundary.
This little spike is then supposed to be what controls how fast the whole thing grows.
It's a neat idea, for sure, but it has some, well, fatal flaws. First off, even with our most powerful microscopes, nobody has ever actually seen this spike. Ever. Second, when you do the math, the predicted width of this spike often comes out to be smaller than a single atom. That's just physically impossible. And finally, creating a concentration gradient that sharp would take a colossal amount of energy, making the whole process incredibly unlikely.
Okay, so the spike model is a bust. What's the next contender? It's a theory called solute drag.
The solute drag idea suggests that certain atoms are attracted to the moving boundary and have to be literally dragged along with it, which slows it down. But here's the thing. That requires those atoms to actually pile up at the boundary. And remember that atom probe data we just looked at? It shows that simply doesn't happen. The atoms are frozen. On top of that, bainite forms at such low temperatures that atoms can barely move. Get this, at 300 degrees Celsius, it would take an atom of nickel 10,000 years to make a single jump. There's just no way they're dragging anything.
So, with the solute spike being physically impossible and solute drag being directly contradicted by the evidence, the displacive snap theory is the only one left standing. The evidence is conclusive, the case is closed.
So you might be thinking, okay, that's a cool science puzzle, but why does solving this decades-old mystery actually matter? Well, it matters because understanding how something works at this fundamental level is the key that unlocks a whole new world of design.
And this isn't just theory. As Professor Bhadeshia, the author of our source material, says right here, this deep understanding has directly led to the creation of brand new commercial steels, including the world's first bulk nanostructured steel. That's huge. And this is the critical shift. We've moved away from just discovering materials through trial and error to being able to intentionally design them right from the atoms up. By controlling this transformation, scientists can create these incredibly fine, complex microstructures, just like the one you see here, to get properties we used to only dream about. And that has massive implications for the real world. We're talking about creating lighter cars that are more fuel efficient, but also safer in a crash. We're talking about building bridges and buildings that last longer and can handle more stress. This tiny, microscopic understanding leads directly to huge macroscopic improvements that affect all of our lives.
So you see, solving the Bainite puzzle wasn't just some academic exercise. It was about cracking the fundamental code of steel. And it leaves us with a really exciting final thought. If we can now design steel with this amazing level of precision, what other supermaterials are out there, just waiting for us to engineer them atom by atom to build our future?